Hello and welcome to video lecture of chapter 30. As you all know, this is the last chapter that we will be covering this semester. It will go for 2 weeks, so this is the first week of that. My plan is to cover the entire chapter within this one video lecture. My advice to you to please, if you haven't read the chapter yet, please stop the video, go back to the book, and please read the entire chapter. Make sure that you have a general understanding, a broad understanding of what it is, and then come back and watch it. The concentration of this video is going to be on solving problems. I will be bringing some examples from my own lecture notes, and I will be solving maybe a couple or 3 problems from the homework problems. Okay. So anyway, let's begin. Like I said, I am going to be brief in terms of explaining things, and I will be concentrating mainly on solving problems. Okay. Okay. As you may remember, for those of you who've read the chapter already, there is a way to measure the nucleus, and that is given by this formula right here. It's got the radius of the nucleus is given by that. I'll talk about it in a sec. Of course, I'm sure all of you have taken chemistry classes, probably more chemistry than I have. So you are familiar with the atomic number and the mass number. So for any typical nucleus, let me go to. So any typical nucleus, let's call it X. You have the mass number A, and then you have the atomic number and the neutron number, right? And of course, A is equal to Z plus N, okay? This is the number of neutrons, number of protons, and when you add them up together, you will get the total number of nucleons. There is another name when we say the word nucleons. Here we mean either protons or neutrons, okay? It's a general word that describes both of them, okay? Nucleons, okay? And of course, we know that the nucleus, when we say nuclear physics, we mean why we call it nuclear physics? Well, because there's another branch called atomic physics. Atomic physics is the study of atoms. Nuclear physics, the study of nucleus. The particle physics, the study of subatomic particles. Molecular physics, the study of molecules, and so on. So we specialize, nuclear physics specializes in the study of the nucleus of the atom. Okay, and the classic picture of a nucleus is to think of it like imagine you have think of it like a bag or a sack where it is filled with nucleons. Okay, so you got protons here and neutrons. They're not necessarily equal, as you may know. Okay, so you have Z plus N. Their total number, the total number of those nucleons, is the mass number. What chemists would call the mass number. Got it? Okay. Then for a nucleus, again, this is the classic picture of a nucleus. It's not really the correct picture, but we will accept it for now. If you take advanced courses in nuclear physics, the picture becomes very, very different. Anyway, so let's say I have a nucleus, any nucleus, okay, and we have an empirical formula. It is right there, this one right here, see it? It says that this formula basically help you or allows you to measure the approximate radius. This is not an exact radius here, the approximate radius of the nucleus. And this radius of the nucleus is equal to R naught A to the power of 1/3. Okay? What does that mean? Well, let me just say that R naught here is a constant, and it is equal to 1.2 femtometer. Okay? Now, a femto is 10 to the negative 15. Okay? So femtometer, this means it is equal to 1.2 times 10 to the negative 15 meters. Okay? Okay. So, for example, let's pick an atom or a nucleus. Let's say carbon. Okay, and of course carbon is carbon 12, right? Which is A equals 12 here. So I'm curious to know what is the radius of the carbon nucleus. Okay, so simple. So all I need to do is just R equals to R naught is 1.2 femtometer. multiplied by 12 to the power of 1/3. And you just plug it in. I'm going to use my calculator here. So this will be 12 to the power of 333, and multiply this by 1.2. Answer, if I did it correctly, the radius of the nucleus of the carbon is 2.75 times 10 to the negative 15 meters, which is basically 2.75 femtometer. You got that? That's the average. This is the average radius, approximately, nothing precise here. Approximately, this is the average radius of the, of course, we talk about also the diameter of it. So the diameter, so if I have here, if I am picturing the carbon nucleus to be like a ball or a bag, like we said here, so the domain or the width of it or the diameter of it is roughly 5.5. So that's roughly 5.5 femtometer. Got it? And that's basically what it is. Okay. Good. The next topic is the isotope. And I am assuming that you've already read the chapter. You know what the meaning of the word isotope. Very important word. An isotope is basically an element or the atom that has the same Z but different N, the number of neutrons. I'm going to show you usually when I teach this course, this chapter in class, I would have given you this handout, but I have already scanned it and I'm going to post it in class. So please, look it up and keep it handy whenever you need it. There it is. Basically, this one page, I photocopied it a long time ago from a nuclear physics textbook. And basically, this is just, this is the first page of this is called Appendix D, Table of Atomic Masses. And there are a total of something like 20-30 pages. This is just page 1, okay? So as you can see in this one, let me get it bigger a little bit. I hope you're able to see it. There we go. Okay. So for example, look at, forget about these for a minute. We'll come back to all these numbers that I have written, handwritten later. But this is basically, think of it like the periodic table, right? Hydrogen, helium, lithium, beryllium, boron, carbon, and so on. But this is the table of isotopes, okay, or nuclei, which basically, here, hydrogen, helium. This is the periodic table, hydrogen, helium, lithium, beryllium, boron, carbon. There they are, okay? But each atom here has isotopes, okay? So here they are. For example, if I get it bigger a little bit, notice, for example, say helium. The one in the periodic table is helium-4, okay? But there is a helium isotope 3. What does that mean? It means Z, the Z is always the same, okay? Z is the identity of the element, but the number N is different, the number of neutrons. So here we have A equal 3 because, remember, N is A minus Z. Okay, so these are all isotopes. The one in the periodic table is helium-4. Lithium, for example, I think it's 6. Lithium-6 is on the periodic table, but the other two are isotopes and so on. Okay, so they have different number of neutrons. Okay, a lot of the isotopes, not all of them, but a lot of them are unstable. Okay, so radioactive. Then you get, so this is basically, then the last column here is the abundance or the half-life. The abundance means, for example, let's look at, let's say, for example, hydrogen, okay? So we have here 3 isotopes of hydrogen, okay? Of all of them, it turned out that hydrogen 1, the one in the periodic table, is 99.9855 or 58, whatever, percent abundance, which means the rest of it, minus 100, is the other two here, this hydrogen 2 and hydrogen 3. So they don't really exist much in nature. For example, hydrogen 2 only make up 0.015% of all the hydrogen atoms in the world, in the universe. You see what I'm saying? Okay, that's the meaning of that. Okay, let me go back. Okay. And another thing is we also measure the masses, the atomic masses here. We have the mass of the proton and the mass of the neutron, okay? And we use the, in terms of kilogram, the mass of the proton is 1.67262171 times 10 to the negative 27 kilogram. You don't need to write this one down. And then for the neutron, it's slightly larger, 1.67, I'm copying it here, I'm not memorizing it, 2728 times 10 to the negative 27 kilogram, and so on, okay? We write the atomic masses in nuclear physics in another unit. We call it the atomic mass unit, the AMU, the atomic mass unit. It's in the book. You can read more about it, but I'll just be very brief here, okay? One AMU, your book uses the symbol 1U, okay, not AMU. I like AMU better. Okay, 1 AMU is equal to 1.66 times 10 to the negative 27 kilogram. Okay, it's a very convenient unit to use. Okay, so 1 atomic mass unit is equal to that. So if I look at the masses of the carbon and the neutron, excuse me, the masses of the protons and neutrons, and I want to convert them to atomic mass unit, it turns out that the mass of the proton is equal to 1.007825 AMU, and the mass of the neutron is equal to 1.008665 AMU, and the mass of the electron is equal to 0.0054858 AMU. Okay, and finally the mass of the hydrogen atom. Well, what is hydrogen? Well, hydrogen atom, you have a 1 proton, right? And then you have an electron going around it, right? That's the hydrogen atom. So in this case, the mass of the hydrogen atom, the mass of the hydrogen atom is basically the mass of the electron plus the mass of the proton, correct? Well, here's the mass of the proton, here is the mass of the electron. So the mass of the hydrogen atom is equal to 1.007825 AMU. You got it? Okay, basically, let me go back to the handout, that scanned sheet, and let me magnify it a little bit. I have them all written down here. Like I said, I'm gonna post it in the course somewhere. I don't know yet where, but so it's going to be handy for you. But anyway, here is the mass of the proton right there, the mass of the neutron, the mass of the electron, and then the 1 AMU is equal to 1.66 times 10 to the negative 27. You got that? Okay. One more thing. Right now I'm just building up some data before we start working on a problem. So let me go back to okay. In previous chapter, you studied the famous equation E equals mc squared, and you've learned that you can convert mass into energy, right? And how you do that? Well, just if you have a mass of say 1 gram, so how much energy is that? Well, it's mc squared, so it's just 1 times 10 to the negative 3 kilogram, right? Times c squared, just 3 times 10 to the 8 squared, and then you calculate that. That will be something like 10 to the negative 3 times 9 times 10 to the 16. So that will be 9 times 10 to the 13 joule. Got that? That's how you. So if I have 1 gram of matter and I convert it into heat, I will get this much heat or whatever energy you're dealing with. Okay? A huge amount of energy. Now, in nuclear physics, we deal with this formula, but because we are using AMU for mass rather than kilogram. You see what I'm saying? So we don't use the speed of light c squared. What we do is the following, okay? We deal with the following. This c squared is equal to 931.5 mega electron volt per AMU. What does that mean? It sounds complicated, doesn't it? Okay, what that means, if I want to calculate the energy of something, okay, which is mc squared, all I need to do is first convert the mass into AMU. So if you have it in gram or kilogram, convert it into AMU. That's the first thing you do. Second, take that mass, multiply it by c squared, right? But c squared is equal to what? Is equal to 931.5 MeV per AMU. What that means, your answer, you're done, basically. Your answer, your final answer, is going to be energy equal a number, MeV, mega electron, not in joule. We're not interested in the unit joule, okay? In nuclear physics, we deal with mega electron volt, okay? So you'll end up with that. Let me give you a quick example. Let's say, for example, I have, let's say I have a mass, let's say the mass of the proton. So the mass of the proton, 1.67 times 10 to the negative 27 kilogram. Well, the mass of the proton in AMU, which is, you divide that by 1.66 times 10 to the negative 27, or I can just go back here, and it is, it's right, oh God, there we go. Mass of the proton is 1.007825 AMU. You see that? Let me go back to that. So this becomes 1.007825 AMU. If I want to know the energy, okay, if I want to know the energy, in other words, just like I did that with remember that 1 gram that I am talking about here, and I convert it into energy? So 1 gram gives me 9 times 10 to the 13 joule. Well, what about if I have this much mass in AMU? How much energy is that? Simple. All you need to do, again, it's the same formula, E equal mc squared, but we're using those funny units, so it becomes m, which is now 1.007825, multiplied by c squared, but c squared now is this one. Got it? So 931.5 multiplied by that. So we have here, so it becomes 1.007825 times 931.5. Answer 938.8 mega electron volt. There it is. You got it? That's how you convert it. So from now on in this chapter, we don't deal with c squared as 3 times c as 3 times 10 to the 8. We don't deal with this at all, okay? We basically deal with this number. Keep that in mind. This is very, very important, okay? All right. Now, we talk about, now the next topic is the binding energy, which is one of the first topics in the chapter that is really important. The binding energy. Basically, the energy that binds the nucleons together, right? So, how do we calculate it? Simple. The binding energy is this. Let me talk about something else before I do that. There's something called the mass defect. I apologize for those honking outside. I live close to a private school, and I have no idea. They have some activities going on there, and I see the teachers are standing on the sidewalk, and then the students are in their cars. They're not allowed to shake hands, and the students are just honking, and the teachers are waving to them. This is just crazy. It's been going for like 2 hours. Anyway, I closed all the windows, but still the noise still come in. Anyway, so we have something called a mass defect. What that means is this. Let me give you a simple example. Let's say, for example, you have a bunch of stuff, a lot of things. Let's say you have an eraser, okay? Let's say you have a key, and let's say you have a pen, and what else? Whatever else. Let's see. I'm looking at around my. Let's say you have a watch, whatever it is. Okay. Let's say you have a hand watch. Okay. Assume that you get those 4 items. Okay. I'm going to weigh every one of them. Eraser. Let's say it is 100 gram, or whatever unit you want. It really doesn't matter. Let's say the key is 50 gram, and the pen is, let's say, 70 gram. And the watch is 150 gram, okay? So now I am weighing them separately, okay? So I'm getting those masses for these items. What is the total mass here? Well, it's going to be 200, what is that? 200, 300, 370 gram, right? Got it? Easy, right? So if I measure the mass of each separately, and I record their masses, there they are, then I add them up together, I get the total mass of 370. Now, however, if I take those 4 items and put them all in one shot over the scale, all of them together, the bulk of them, put them on a scale, I will find out that they are not 370, but they are, say, 369 gram. Again, this stuff doesn't work for regular thing. We're talking here about atoms, okay? It doesn't work for real life. And in real life, of course, it's going to be 370, okay? But anyway, so you got to get, so it's like, what's going on here? You have a missing 1 gram mass. What is it? Do you see what I'm saying? And that's the meaning of the term, the mass defect. Okay? So you have a defection of mass here. Of course, it doesn't apply in real life to the key and the eraser and the watch. It applies to atoms, okay? What happens is that this mass, this defect, this deficiency in mass, actually converts into energy to bind the nucleons together. They call it the binding energy. You get that? In other words, if the mass defect says delta M, if I want to calculate it, is basically the total number of protons times the mass of the proton plus the total number of neutrons times the mass of the neutron minus the mass of the atom, the mass of the nuclide, okay? When I subtract those two together, minus the mass of the atom, I will get the amount of mass deficiency, and that deficiency converts into energy to bind them together. Let me give you an example. Let's apply it to deuterium. So what's a deuterium? Deuterium is basically Z equals 1, N equals 1. What is it? I'll go back to it. I think I have it here. There they are. The deuterium is right here. Do you see? Here is it's basically it says Z equal 1, N equals 1. Here is Z equal 1 and N equals 1, which is basically that. So it's I'm sorry. What is Z equal 1? N equals 1. Yes, sorry. It is A equal 2, because Z equal 1 and the neutron is equal 1. So the 1 plus 1 is 2. So basically it's this one right here. So it's a hydrogen, but you remember hydrogen atoms, they have what? They have 1 proton, right? But this one has a neutron. So 1 neutron, 1 proton, and you will get this. So the atomic mass of this deuterium is equal to, or deuteron, sometimes called, is equal to 2.014102. Got it? Okay. All right. So if I look at the table, so the mass from the table, which is this big M right here, is 2.014102, okay, AMU. And of course, now if I want to get the delta M, the mass defect, well, it's basically what? The mass of the hydrogen atom, which is basically this one. See this? I forgot to mention. See, the number of protons times the mass of the proton, that's basically the mass of the hydrogen atom. Make sense? Because what's the mass of the hydrogen atom? It is the electron, one electron, and one proton here, right? Going around. Well, that will be it's in the tables is basically that, okay? For the hydrogen. So it's the mass of the hydrogen atom times, maybe I should make myself a little bit more clear, Z times the mass of the hydrogen atom, plus N times the mass of the neutron, minus the mass of the deuteron. Well, this is the mass of the deuteron right here. So that's going to be 1 times the mass of the hydrogen atom, which we can go back to the table and look it up. I have already shown it to you, 1.007825, plus 1 neutron, and the mass of the neutron is 1.008665, minus the mass of the deuteron, which I already looked it up, it's equal to that, minus 2.014102. And then you do the calculation here, you'll end up with this, 0.002388 AMU. Okay, there it is. Got it? So here is delta M. This is the mass defect. This is the missing mass, if you will. What happened to this mass? This mass converts into energy, binding energy to be more exact, to glue the neutron and the proton. In other words, here is how the deuteron look like. The atom, excuse me, the nucleus. It got 1 proton and 1 neutron. That's it. And they are glued together. How are they glued together? They're glued together by the binding energy, Be. I like to call it Be or big B. Okay? And this binding energy is equal to mc squared. But this M is the mass defect. Delta M is this one. So if I want to calculate the binding energy, it's nothing but delta M c squared. So it's become 0.002388 times c squared, which is 931.5. Remember? We calculate that. Of course, let me just be MeV per AMU. And then that will give me 2.22 MeV. And that's the binding energy of the deuteron. Got it? Everybody got that? Okay. Here's another example for calculating the binding energy. Find the mass defect, binding energy, and binding energy per nucleon. Okay, there's a symbol for that. I'll come back to it in a sec. It's basically that, really, binding energy per nucleon over A. Okay, I'll come back to it. Okay, for carbon-12. Okay, which is the most common isotope. What is carbon-12? Let me go back to that thing. Carbon-12, which is carbons for the atomic mass 6 right here, right? Let me make it bigger. Right there, and see that? Here is carbon right here. Carbon-12 is right there. And the atomic mass of it is the simplest mass, 12.0000. It's exactly 12, okay? The abundance is 98.85 or something like that. Okay, I have the hard copy here. It looks much better than the one you're looking at. It is 98.89%. Okay, so that's basically what it is. But the number that we need is the mass of it, which is 12. You got that? Okay. All right, we want to calculate the mass defect. Well, the mass defect is what? Delta M is equal to, let's just write down the formula again, Z, mass of the hydrogen, plus N, mass of the neutron, minus mass of the carbon, the one you found in the table, okay? The one I just showed you from the table. You got that? So, okay, so let's do it. So we have 6, we have here, remember when I write it this way, what does that mean? This is Z, N, and A. Some books would write the A here, it doesn't matter, okay? Anyway, so it's going to be Z times the mass of the hydrogen is 1.007825 plus the mass of the neutron, excuse me, the number of neutrons, which are 6 as well, times the mass of the neutron, 1.00866649, minus the mass of the carbon. Again, you go back to the table, what is it? 12 exactly, right? Whatever, like that. And then I do the calculation, and you'll end up with 0.09894 AMU. There we go. That's the mass defect. This is the mass that has been converted into what? Into energy, binding energy. Now the next step, he said, find the binding energy. All you need to do, you take this thing and multiply by c squared. So the binding energy is equal to the mass defect times c squared. So it's going to be 0.09894 times 931.5 MeV per AMU. You calculate that, and you will get 92.16 mega electron volt. This is the total binding energy inside the atom, the nucleus of the carbon nucleus, okay? Now, binding energy per nucleon, it means, okay, let's say here is my nucleus, right? And I have 6 protons and 6 neutrons, right? There they are. Okay, so the total, let me use a different color. The total energy here, the total energy that binds this whole thing together is equal to 92.6. But if I ask the question, each nucleon, proton or neutron, how much energy does it have? Well, it turned out that this energy is divided equally among them. You got it? It's divided equally among them. Well, how many of them in here? Well, it is Z plus N, so that's A. So therefore, the binding energy per nucleon, which means binding energy over A, is all you need to do is you go 92.16 and you divide it by A. A is what? 12. Carbon 12, right? So you just do that, and when you do this, you end up with 7.68 mega electron volt. Okay? That's the meaning of it. You got it? Okay. So the binding energy per nucleus. Now, the highest nucleus with binding energy in the entire periodic table is the Fe, the iron atom. Nickel is as well, I think, right beside it. But anyway, I think I'm going to do an example on that in a minute. Okay. Oh, yeah, there it is right here. Let me just do it very quickly. All right, let's find, again, the same question. Find the binding energy and the binding energy per nucleon for 2. Fe, the iron, and uranium-238. Okay. Now, 238, which means it is 92 for Z. Okay. Fe is the neutron is 146. For the Fe, the iron, it is 30. 26 and 56. Got it? Okay, so let's calculate that. So let's calculate the binding energy directly. So all you need to do is first you calculate the mass defect and then multiply by c squared. You got that? Okay, so for Fe now, let's do it only for Fe. Okay, so Fe, so we go, remember the formula? Can I write it down for you? Sure, let me write it down. Zm sub h plus Nm sub n minus m the mass. All right, that's basically what it is. Oh, times c squared. Remember, c squared here means 931.15 mega electron volt per AMU. Okay, so anyway, let's apply that. So it's going to be, what's z here? 30. 26 times 1.007825 plus 30 times 1.008665, right? Minus the mass of Fe, the iron, and this is something you have to look up. You look up, or in it's usually given to you in the problem. Okay, you're not required. It's not in the table that I'm supplying to you, but it's usually given to you. And when you look it up, the mass of the atomic mass, you just look up the atomic mass of iron. You can actually Google it. Just write atomic mass of iron. You'll get that number. Here is the number that I have: 5.934937. And there we go. You take that and you multiply that by what? By C squared, which is 931.5 MeV per AMU, right? Everybody got that? Then we just plug it in, and you'll end up with a whopping 492.3 mega electron volt. This is the binding energy for iron. It is the largest in the universe, by the way. And binding energy per nucleon, it's basically you just divide that by A. A is 56, right? So 492.3 over 56. And when you calculate that, you get the largest binding energy per nucleon for any nucleus. Binding energy per nucleon. Okay? Mega electron volt. Okay? So this is the most tightly, if you will, bound nucleus. Got it? Okay. So there we go. That's the binding energy per nucleon for the iron. Let's do it for the uranium. Uranium 238, 146, and 92 here. Okay. So we can do that. I'll do it very quickly. You know how to do it now. You know the drill. So it becomes 92, 1.007825 plus 146, 1.00865 minus, again, look up the atomic mass of uranium. Okay, let me show it to you on the web. I mean, just in case. I mean, atomic mass. Here, for example, here, since it's atomic mass of iron, and there it is. See the number? It's right there. It comes out very quickly. Atomic mass of uranium, and of course there are several isotopes. You need to be careful. This is for uranium-238, and that's the one we're dealing with, uranium-238, and it's equal to this, 0.02. Now, here is the interesting part. Each lab or standard agency that comes up with those constants, they are different. So you may want to stick with what the book is telling you. Okay. For example, the one I have, the number that I have here. Let me just leave it here on the side. And I'll show you the number that I have. Again, this is nothing to be worried about, but here is the atomic mass of uranium. Here is the one I got it from my note, my book, which is a nuclear physics book, Kenneth Crane. That's he's considered the Bible of nuclear physics, and he says the atomic mass of uranium-238 is 238.0. So far is the same as this one here. 0.50788. See the difference? See this discrepancy? So there is a slight difference there. So you want to be careful about that, okay? Nothing to worry about. You will usually it's given to you, like I said, in the problem. No one expects that you are, you have to memorize those numbers. Well, nobody does. Anyway, times 931.5. And then you just multiply this whole thing. You're going to get 1,802 that's it, MeV. Okay? And then the binding energy per nucleon for uranium, which is a little bit less. It's not as tightly bound as the iron. So you're going to take that 1,802 divided by 238, and you will get 7.57 MeV per nucleon. Okay, good. Okay. There is another example, the same stuff here. I'm going through my lecture notes. Okay, now we jump to the next topic, and that is radioactivity. you know, unstable nuclei, and I hope you will take the time to read it. Let me just show you which section is that. Sorry, bear with me. Radioactivity, section 30.3, okay? Okay, so all unstable nuclei disintegrate, and when they disintegrate, they emit a certain particles. There are three types of disintegration, or three types of emissions, or rays they call it, okay? One is called the alpha emission, or alpha decay, beta decay, and gamma decay. I'm going to go over those, every one of them, briefly, okay? Again, read from the book. Read all that from the book. He talks about them. He gives you, they're not very long. I can see that just a quarter of a page is the alpha, and the beta is about half a page, and so on, okay? It's not very long. Okay, the alpha decay, this alpha is nothing but a helium nuclei, okay? So the helium, which is 422, okay? Nucleus, not the whole atom, but only the nucleus. So you have a helium nucleus that has 2 protons and 2 neutrons. You see what I'm saying? And this, so it basically you have this big giant nucleus, such as uranium. Okay, uranium is the largest atom. It has 100. I mean, we have uranium 238, right? So these are 238 nucleons. So there are 238 here. You see what I'm saying? Of those, uranium. So 146 neutrons and 92 protons. You see what I'm saying? So a very, very large one. Okay? And it is, by its own nature, is unstable. So what will happen eventually? It will just emit this particle, the helium nucleus, what we refer to as the alpha particle. Okay, it emits it. So what happens when it emits it? Watch this. That's basically what alpha decay is. So it's the emission of an alpha particle, which is helium. And usually this emission is usually done by a nucleus that is very heavyweight, very large nucleus. You're not going to expect an alpha decay from, say, carbon nucleus. Carbon is really small. It's only 6 protons, 6 neutrons. They're very small. It will, no matter how radioactive it is, it's not going to emit an alpha particle. Alpha particles only happen to really large, such as uranium, thorium, plutonium, and so on. Okay, these are big, giant ones. And specifically, to be more exact, when Z is larger than roughly 80 or 84 or something. Okay, these are large. You get this heavyweight nuclei, and those you would expect it with a higher probability to emit alpha particles. Okay, now the middleweight, which is somewhere, so say for example from Z is equal roughly 20 up to about 80, you will get the beta. We'll talk about the beta in a minute. Okay, so anyway, so what will happen? So let's say I have a heavyweight nucleus right here, Z. So it is A and Z here, right? X, sorry. Okay, so when it disintegrates, it becomes something else. We're going to call it Y, and what will happen to it is that when it disintegrates, because see, it is emitting a helium nucleus 422, so that means this N is going to subtract by 2 because the helium will take 2 neutrons, and the Z will subtract by 2, and A in this case will subtract by 4. So it becomes something like this. Z minus 2, N minus 2, and A minus 4. Okay? You got that? And we call this, the original one, we call it, in the jargon in nuclear physics, we call it the parent nucleus. This is called, we call it the daughter. Okay? The resultant one. This is the daughter. And of course, this is just the alpha particle. the emitted particle. You got that? Okay. So when this happens, I mean, a perfect example of that is you have a uranium. You have a uranium-238. Okay, and this uranium-238, it disintegrates or decays into thorium. Okay, and thorium is 234 and 90 here. Remember, this is 146 and this is 92. And what is it? 144, is that right? Plus an alpha particle. Got it? Okay. So what I want to do is I want to calculate the energy that is accompanied by that. Remember, the decay is always accompanied by energy, excess energy coming out in the form of heat, and which is basically the kinetic energy for the emitted alpha particle, and the daughter. Okay, so there is a plus energy. I'll just say here. Okay, this I want to calculate this energy. Well, the energy here is basically, again, you want to get that mass defect again. What you do, you get the mass of the daughter plus the alpha particle, and also you get the mass of the parent, and you take the difference between them. Basically, the difference between the daughter and the alpha minus the mass of the parent. You got it? So the mass defect here is the mass of the daughter plus the mass of the alpha minus the mass of the parent. Okay? And then when you calculate that, you will get the mass defect, and then you can, from this you can get the energy. Well, how do we get the energy? Well, it's mc squared. Delta mc squared. And c squared, of course, is again 931.5. Got it? Okay, so let's do a real example on that, which is the uranium. So here we have the uranium-238 becomes the thorium, what is it? 234 plus an alpha particle, okay, plus actually a gamma, but the gamma is so small we kind of neglect it. I'll come more on it in a minute, but just ignore it for now. Okay, so let's calculate that. So before I do that, let me just show you, again, if I look up the tables for the masses, the atomic masses of those three, the atomic mass of 238 is 238.0508. The mass of thorium is 234.0436 AMU, and the mass of the helium atom, the helium nucleus, is 4.0026. Okay, and let me show you that very quickly. Let me show you the helium, because it's in this handout right there. Helium, there it is right here. Let me make it a little bit bigger. Right there. See that helium right here? Here's helium 4.002603. Got it? Okay. Okay, 2603. Okay, and then what we do now, all you need to do is you get delta M. So the way we do it, so here the parent is 238.0508, and the sum here, if you add them up together, that is, you will get 238.0462. Okay, then you take the difference between them. So when you take the difference, delta M, by using that formula right there, right here. Oops, sorry. Okay, you take the difference between the daughter plus the alpha together minus the parent. You got it? Okay. And then we do that. So delta M, that is. So in this case, I'll have delta, the mass, is 238.046. 0.462 minus 238.0508, and then in this case we would get 0.0046 AMU. You got it? And then of course you take that and then you convert it into energy, and this energy is delta mc squared, and that will give me 0.0046 times 931.5 MeV per AMU, and that will give me 4.3 mega electron volt. You got it? Okay. Okay, so this is the energy that is that comes after this. So this let me write it down. This is energy appears as kinetic energy, okay, of the recoiling the thorium and alpha particle. Okay. Now the thing is, so in other words, so this energy here, if I can write it, it's basically, if I take the kinetic energy of the thorium plus the kinetic energy of the alpha particle, totally it is equal to the sum would be 4.3 mega electron volt. So which one do you think is taken up more? Do you think the thorium would have more kinetic than the alpha, or the alpha more than the thorium? What do you think? Now remember, the mass of thorium is much, much greater than the mass of the alpha. So this means that the kinetic energy of the alpha would be greater than the kinetic energy of the thorium, right? It's so small, so it's going to take it up and will go faster. Okay. Okay, good. Now we come to the beta decay. Oh, before one more thing I want to mention here. Usually, when you have a beta decay or an alpha decay like this one, when the parent emits, here's the parent right here. When the parent emits the alpha particle, and this becomes a thorium, right? This thorium, this daughter, is actually in the excited state. Remember the excited state in atomic physics and when you studied in chemistry atomic? So it's in the excited state. And this excited state, eventually, if you wait a few minutes, photons will come. Remember in chemistry you studied, you have let's say here's a nucleus, here is energy level, n equals 1, and this is energy level, n equals 2. And if I have an electron here, it goes into the excited state, it goes to energy 2, right? And then when it comes back, what happens? It will emit a photon. You see what I'm saying? Remember that? It emits a high energy photon. I'm sure you studied that in chemistry. Well, we have a similar situation here in nuclear physics, but we're not going to dwell on any of that stuff. But basically, the thorium is in the excited state, the nucleus, not the atom. The nucleus in the excited state, but eventually that photon in the excited state is actually emitted in the form of gamma ray. Okay? So that's gamma ray. That's really what gamma emission is. It's basically whenever you have an alpha decay like this one, or a beta, I'm going to talk about it in a minute, accompanied with that, the daughter becomes in the excited state, and then it loses those photons in the form of gamma ray emission. Got it? Okay. And we don't put them in the calculation because those gamma ray energies are usually very, very small, but they are part of this one. You get that? They are part of it. But again, this is just too much detail. We're not going to worry too much about it. All right, let me move on to the beta. The beta decay. So the beta decay happens when a nucleus is or has too many neutrons. It's actually bloated with neutrons, just have too many neutrons, or it's neutron rich, we call it. and it needs to get rid of one of them, okay? So what it does, it doesn't kick out a neutron. What it does, it does what is called a beta decay. Let me explain it to you. See, a neutron is actually, here's a neutron, okay? It's made out of 3 particles. It's actually made out of a proton and an electron and another little particle that is not important for us is called an antineutrino. Nu, this is the Greek letter nu. This means, the bar means antimatter that is, and it is antineutrino for the electron neutrino, for electron. But anyway, it really doesn't matter. But that's a neutrino, antineutrino. But it's made out of these. Now, the antineutrino really has 0 mass roughly, so we can ignore it. So for practical purposes, a neutron is made out of a proton plus an electron. But we'll add that just for the sake of completeness, but we're not worrying too much about it. Okay, so you have a neutron, it converts into a proton, or it splits, So you have here, you're starting with a neutron here, it splits into a proton and an electron. Got it? Okay, so let's say that I have let's say I have a nucleus, here it is, and it has too many neutrons in it. Okay, now the ratio of protons to neutrons has to be just the right one. Okay, usually the right one excuse me, usually the right one is roughly that the number of neutron to proton is roughly 1.5. Okay, in other words, the number of neutrons exceed by the number of proton by about 50%, give or take. Okay, but if you have something like 1.6 or 1.54 or something, the nucleus becomes neutron rich. So what it does, it needs to get rid of one of the neutrons, or 2, whatever. Okay, so what it does, here is one of the neutrons that are, excess neutrons. Let's say this one here. So what it does, this neutron would convert into a proton, split, it becomes a proton and an electron. But this electron and the neutrino are both ejected out of it. So here's the electron neutrino, antineutrino, and here is the electron ejected. But the proton stays in there. You got that? That's the beta decay. So what you do, what we see in the lab, is that we see those high energy electrons coming out of the sample, and we don't know what they are. And we eventually, later on, we also see antineutrino. They were hard to detect back in the first half of the 20th century. We didn't know about them until the second half of the 20th century. But anyway, in the beginning of nuclear physics, which is the first half of the 20th century, we were seeing very high energy electrons coming out of the sample. It's like, where do they come from? So nuclear physicists refer to them as the beta particles. They didn't know what they are, okay? So they call them, so the name kind of stuck, but they are really beta are nothing but electrons. You got that? They're really the same thing. Except that just that they didn't know what they are in the beginning, so they call them the beta particles. Okay. So symbolically, how does that work? I am starting with a parent nucleus, okay, and it disintegrates into a daughter. And what will happen, this neutron converts into this sum of neutrons. One of them will convert into a proton, and as a result of that, what will happen is that you'll have one neutron less, right? But I have an extra one more proton. You see that? But A is still the same. See that? I still have the same atomic mass, plus the beta particle. Got it? Okay, let me give you an example, show you what that means. You have a thorium, okay, 234, and it is thorium 90. And it is neutron rich, okay? If it is neutron rich, then it converts into the daughter, that is, protactinium. It's protactinium, kind of hard to pronounce, okay? And this is Pa 23491. So you see, it gained, so it's still the same thing, 234, but now it gained one more plus the beta particle, okay? And there we go. This is basically what the beta decay looks like. Okay. So let's have an example with some numbers so we can do it. I have a thorium-234 let me just get the math. We're going to do this one. Sorry, we're just going to do this formula. I forgot about that. So the thorium, if you look up the table, is the mass of it 234.04359 AMU, and the protactinium is 234 is 234.04330 AMU. So now, if I want to calculate delta M, so you just take the difference between them, okay? Now, the difference, you can switch between daughter minus daughter and, daughter and electron minus that or that, and to such a way that you get a positive number, okay? So for our case here, we're going to do, if you take the difference between them, you will get this 234.04359 minus, you add them up together, so that will be 234.0433. That's for those together, okay? And when I calculate that, I get 0.0029, sorry, 3 zeros. Let me fix it, sorry. 0.00029 AMU, okay? And as a result of that, we can convert it into energy, and this energy is equal to, multiplied by 931.5 MeV over AMU, and then this will give me roughly 0.27 mega electron volt. Of course, it's in the what? It is the maximum. You can think of it like the maximum kinetic energy of the emitted electron. Okay? Or energy release. Of course, there is a second kind of beta decay, which is the positive beta decay. If you have a nucleus, second kind, is beta decay. If the nucleus is neutron poor, in other words, it needs more neutrons. Sometimes it happens that way, okay? So it needs more neutrons. So what happens in this case? Well, here is the nucleus, okay? Here are the nucleons inside, and let's say there are just too many protons in there, and it needs to convert one of those. So what it does, it takes one of those protons and it converts it into a neutron. It works like that. Here is a proton. It becomes a neutron plus a positive electron called the positron plus the neutrino, not an antineutrino, but a neutrino. Again, we are not worried about this one, okay? All right. And of course, like I said in the past, let's go back regarding gamma. So let's do this formula right here. I'll put a different color here. So we're starting with the thorium here. This is the beta decay, right? And then the daughter becomes a protactinium right here. In the excited state, all these decays always leave the daughter in the excited state like that. And then after a while, depends, a minute, a second, a nanosecond, whatever, it would emit a gamma ray photon. So this is always at plus gamma. You get that? So this energy that we have just calculated, that includes the energy of the electron, and maybe the energy of the daughter, and also the energy of the gamma. You get that? So that's basically what the gamma decay is. So we don't really do a lot of calculation for gamma because it's not terribly important. It actually requires some quantum mechanics to do that. But here is the gamma decay. So you have a nucleus in the excited, the star means excited state, okay? So it is E and Z, and it becomes basically the same nucleus in the stable state, the ground state, plus a gamma emission. That's it. Okay, that's all you need to know about gamma. Okay, good. Moving on. The next topic that I want to talk about is the decay, what is called as the decay rate. Let me show you the color. Here, we have just finished talking about the radioactivity at the atomic level or at the nuclear level, where you have one nucleus, ejecting an alpha particle or a beta particle, or the daughter becomes in the excited state, and then it would go to the ground state by emitting a gamma ray emission. You see what I'm saying? Now, what will happen if I have a sample? I'm talking here a sample that I can, a sample of an n number of nuclides. Okay, I mean, I'm talking here in terms of, let's say you have 6-7 grams sample, a macroscopic sample. Okay, before I talk about that, we define what is called the activity rate. The rate of activity, R, okay? And this R is equal to lambda n. Again, please take the time to read from the book. This is on page, Decay Rate, page 970. I'm just going to be brief here. I'm going to give you the basic formulas, and then we'll start doing some problem. So this is called the activity rate, and it's equal to lambda n. N is the number of nuclei, and the R here is the decay rate, the activity rate, and this is called the decay constant. Lambda here is the decay constant. I like to call it the probability constant. And it's a unique number for any radioactive sample. Another formula that is important if I have an n number of samples, I'm starting with some number of samples, okay? After some time, and it's decaying with whatever kind of decay, whether it's alpha, beta, or whatever, and it's decaying. After some time t, it will become n, and it's equal to n naught e to the minus lambda t. Okay, this is known as the decay rate. Okay, it looks something like that. The way samples decay, if I'm going to graph this one, it will look like a decay graph, which is an exponential decaying graph like this, where this is the time axis, and this is the number of sample at any time t, and this is we're starting at t equals 0, n naught. Okay, this one here. Got it? Now, the time it takes for the sample to be half the original, which is right here. See, this is n naught over 2. That time is called the half-life. And we have a symbol for a t sub 1/2. Okay? Now there is a link between the decay rate R equals lambda n and this formula right here, and it's given by the decay activity, or the activity rate is equal to R naught, the initial activity, e to the minus lambda t. That's another formula. I'm just going to put in the formula, then I'll show you some examples. Also, there is a way to calculate the half-life, and it's equal to natural log of 2 over lambda. Okay, let me derive it for you very quickly. I mean, from the definition, the half-life is what? The half-life is the time it takes for the sample to go from n naught to n naught over 2. So if I use this formula right here, so it becomes n naught over 2 equals n naught e to the minus lambda t. And what I'm going to do, I'm going to solve for t, right? Solve it, let me do a different color. Notice that the n naught cancel out. I end up with 1/2 equals e to the minus lambda t. Take natural log to both sides. That will give me that, right? And then I'm going to solve for t. That will be natural log of 1/2 over minus lambda, right? Well, natural log of half is equal to minus natural log of 2 over minus lambda. I hope you know your algebra. The minuses cancel out. So t 1/2, we define it to be this with this symbol, is equal to natural log of 2 over lambda, or natural log of 2 is 0.693. I've always memorized it, over lambda. Okay, so that's basically, this formula can also be written as 0.693 over lambda. Okay. One more thing. Again, this is all in the book. Please read them. Read the information. We have units here. We define the Curie. This is a unit, a very common unit in physics, in nuclear physics. 1 Curie is equal to 3.7 times 10 to the 10 decays per second. Okay? And 1 decay per second is called 1 becquerel. 1 becquerel. Capital B, small q. Okay? The becquerel, BQ, the spelling of it, BECQ-UEREL. The becquerel. Okay? After some physicists by the name Becquerel. So, in other words, if I use becquerel, so 1 Curie, which is CI for Curie, is equal to 3.7 times 10 to the 10 becquerel, because decay per second, 1 decay per second is 1 becquerel. So this is an important relation you want to keep in mind, that 1 Curie is 3.7 times 10 to the 10 becquerel. Okay, let me give you an example. Let's do some problems now. These are examples from my notes. So I have the element radium, has the symbol Ra. It has a half-life, or the half-life, I know, T sub half, is equal to 1.6 times 10 to the 3rd years. Okay, that's the half-life. The time it takes it to lose half of its sample. Okay, now if, says the problem, if a sample contains initially n naught equals 3 times 10 to the 16 nuclei. Question: what is the activity at this time? What time? I'm sorry. Oh, okay. So given this was at this time, basically what he's looking for is R naught. Okay. So if you remember, R naught, we define R naught to be equal to. I'm trying to find it here. There it is, right here. Right. So for our case, R naught will be lambda n naught. See what I'm saying? Make sense? Okay. So R naught, let me read the problem again. Let me just make sure that all of us have read it. So we have a radium Ra. It has a half-life of this. And it contains, initially at t equals 0, it contains this many nuclei in there, 3 times 10 to the 16 nuclei. And we want to find R naught. I know that R naught is equal to lambda n naught. I already know what n naught is right here, right? I need to find lambda. Well, how do I find lambda? Well, we know that T half-life is equal to 0.693 over lambda. So therefore, lambda is 0.693 over the half-life. Okay. Now, this one thing is very important. Always the half-life is in seconds. Never use it's given to us in years, but you have to convert it into seconds. How do I do that? I know that 1 year is equal to 3.15 times 10 to the 7 seconds. Okay? You may want to write it down somewhere because it's going to be convenient for you to convert. So in this case, given this half-life in years right here, so I have to convert that first before I use this formula. So T1/2 is going to be equal to 3.15 times 10 to the 7 multiplied by the number of years, 1.6 times 10 to the 3rd. When I calculate that, I get 5 times 10 to the 10 years. Seconds. So this is the half-life right here, okay? I take that, now I'll plug it back in here to get the probability constant lambda, the decay rate. So 0.693 divided by 5 times 10 to the 10, and the decay constant is equal to 1.4 times 10 to the negative 11 decays per second. This is the probability, got it? So therefore, the activity, which is R naught, is lambda N naught. So lambda is 1.4 times 10 to the negative 11 multiplied by N naught, which is given to us above, right there, right here, right? And that's equal to 3 times 10 to the 16. We calculate that. I thought I have it with it. Oh, there it is. Okay. So we will get 4.1 times 10 to the 5th decays per second, right? Now, what is decay per second? Becquerel. So I can write it as 4.1 times 10 to the 5th becquerels. Got it? Okay. This is R naught, the activity rate. Now, what if I want to do it in Curie? So we know that 1 Curie is equal to 3.7 times 10 to the 10 becquerels. So therefore, R naught, you do the conversion, it will turn out to be 11.1 microcurie. Please convince yourself that this is the correct result. It will be that. Got it? Okay. Next example. I have radon. I don't know if you remember radon activity of radon gas. You know, radon, you find them in the basement of homes, and it's radioactive. So I have a radon gas. It is Rn 22286, okay? And the half-life of the radon given to us is equal to 3.83 days, okay? So it is radioactive, more radioactive than the one we just dealt with, okay? And the question is, okay, we have a gas sample N naught equals to 4 times 10 to the 8 radon atoms initially. Okay, now there are A, B, how many parts? We have 3 parts, A, B, and C. A. How many is the question? How many will remain after 12 days? Okay, how many will remain after 12 days? Given that this is the half-life of it, and we're starting with this one. Those are the information that is given to us. Okay, so one way to do that is how many will remain after 12 days. Basically, the formula that I have in mind is this one. N equals N naught e to the minus lambda t. This is given to me, N naught, right? And after 12 days, that means this is given to me, t. And he's asking for how many, which means N right here. So first I need to find lambda. You see what I'm saying? And I know lambda is equal to what? 0.693 over the half-life. Again, the half-life is written in seconds. So I can do that quickly. And that will be equal to, you know what? I'm doing it in days. Let's just do it in days. We can do it in seconds. Hold on, sorry. Yeah, I got it in days for a good reason. Let me stick for days now. So it becomes 0.693 divided by half-life in days is 3.83. And when I do that, it will be equal to 0.181 decays, not per second, but per day, correct? Because I am using days here. The next step, so now I got the lambda, so now I can easily get it here. The reason, you'll see in a minute why I kept it in days. Now I go back to this formula. So I have here N equals to N naught e to the minus lambda t. So N naught is given to me right there, right here, 4e8. So that's going to be 4 times 10 to the 8 times e minus 0.181. Remember, it is decay per day, correct? Times 12 days. Do you see the trick? The days cancel out. So even if I convert it to second, I'm stuck of converting the 12 days to this. So this is kind of a trick. That's why we just kept it in days, because the day is going to cancel out anyway. If we put them in second, they're going to cancel out anyway as well. So that's why. But as a standard thing to do is the lambda is always in seconds. Keep that in mind. Okay. So anyway, so we have this. So we have 4 times 10 to the 8 e to the minus 0.181 times 12. Whoops. And when we calculate that, I end up with 4.6 times 10 to the 7 atoms. There we go. Got it? So I'm starting with 4 times 10 to the 8, and now after 12 days, I only got 4.6 times 10 to the 7. Got it? Okay. Next part, A, B, and C. What is the initial activity, R. Activity. Initial, which means what? R naught, right? Activity of the radon sample. Okay? Well, I know that the R naught is equal to lambda N naught. Now I know lambda, but remember, activity is always in seconds. So lambda is what? Well, we already got it, sorry. Lambda, we got that already, didn't we? Thought we did. Yeah, it's right here. Lambda is equal to this number right here, right? This is lambda right here. So let me use that. 0.181. 0.181 decays per day. But I need to convert it into seconds, because this is activity is always in second. You got that? So how do I do that? Well, how many seconds in a day? How many seconds in a day? Well, let's see. 1 day, that's 24 hours, times 3,600 seconds in 1 hour. So that gives me, let me use the calculator for now. I have 3,600 times 24 equals 86400. 86400 second in 1 day. Okay? So therefore, lambda is equal to 0.181 over 86400, and that will give me 0.181, I hope you are calculating things with me, divided by 86400, answer, I got 2.09 times 10 to the negative 6 decays per sec. Okay, there's the value of lambda. Now I'm ready to calculate the initial activity, R naught equals lambda n naught. So it becomes 2.09 times 10 to the negative 6 times n naught. What is it equal to? 4 times 10 to the 8, correct? And then we just calculate that, and you will end up with 840 decays per sec, or 840 becquerels. Got it? Okay. The last part of the problem, part C, he said, find the activity of the radon sample, Rn, after 12 days. How do I do that? Well, it is R equals lambda n. You see what I'm saying? Lambda, I already got it. Lambda is a constant. So I know that. And n here after 12 days, I already got it from part A, remember? Here is part A. I got the n right there. You see, remember, it's after 12 days. So all I need is just plug in those two numbers in there. So that's going to be lambda is 2.09 times 10 to the negative 6 times n. What is it? I forgot. 4.6 times 10 to the 7. 4.6 times 10 to the 7. And then when we calculate that, I got 96.14 becquerel. Okay? Okay, good. Just give me a second. I'm flipping the pages here. Maybe let me go to the homework. Let me look at some homework problem. Probably, I think that will be safer. Just look at the homework. I'm not going to do the beginning ones. They look kind of easy. They should be okay. Please, if you get stuck on one of them, just let me know. Just put it under Ask the Professor, and I'll be more than happy to do it for you. Let's see. So many good ones, right? Maybe I'll do number 18. It looks like it has several parts, A, B, and C. Maybe I'll do one more. Hold on. Carbon. Yeah, I'll do the carbon one. Yeah, I'll do number 16. I'll do 16 and 18. How about that? And then we'll wrap up the this video. Okay. This is homework. Number 16. Oh, I need to go to the book. Well, maybe I'll just, let's go to the book here. We are in last chapter of the book. Congratulations, guys. Summary. What is the homework? The 30 should be right here after this one, right? Let me get through this silly thing. There we go. Number what? What did I say? 16. Okay. One more. Right there. Okay. It says, let me magnify it a little bit. Let me just move it to the side. I want to keep it within the frame of the video screen. Should be there. Oops. Okay, let's read it together. It's right here, number 16. Do you see it? Okay, it says a 12-gram sample of carbon from living matter. Oh yeah, the book talks about carbon dating, so please read that. Anyway, so it says a 12-gram sample of carbon from a living matter decays at a rate of 180 decays per minute. Okay? What is that? What would that be? That's the activity rate, R, right? Per minute. You know, it's given not in second, but that's basically the activity rate, R. All right. Due to the radioactive carbon-14 in it. Okay. What will be the decay rate, again, R, of this sample after 1,000 years, after 50,000 years? Okay? Not a bad problem. How do we do it? Okay. So how do we do it? Well, let's look at the data. So what's given to us, the mass of the sample is 12 gram. This is carbon-14. And the initial activity rate, he says, is 180 decays per min, which we don't like. We want to make it into seconds. So it's going to be 180 decay over 60 sec, correct? So it becomes what? 3 decays per second. So that's the initial decay rate. You got that? Okay. Now he's asking, what is the decay rate after what? 1,000 years. Okay, how do we do it? If you go back to the notes, if you've been taking notes, remember we said n equals n naught e to the minus lambda. Here's another convenient one. R equals R naught e to the minus lambda t. Okay? This comes in really handy. I'm sure I've written it up there. But I mean, especially if you're given one of them, find the other, and you're given the time, you know, 1,000 years, all I need to do now is just find lambda first. Once I find lambda, I'm done with the problem. You see what I'm saying? Okay? So let me find lambda. How do I find lambda? Well, I need to find, here is how it, I forgot to mention something. In the book, it's mentioned the half-life of carbon-14. Okay, the book assumed that you already have access to it. The half-life of carbon-14 is 5730 years. Okay, it's not given in the problem, but it's a well-known number. Whenever you read a problem about carbon-14, this is the half-life. Okay, the problem doesn't give it to you, but it's assumed that you can look it up. You got that? Okay. So this is the half-life of carbon-14. Of course, you want to convert it into seconds, so that's going to be 5730 multiplied by 3.15 times 10 to the 7 second. This is how it converts into second. How many seconds is that? So when I do that, let me use my calculator. 5730 times 3.15 E7, answer. So the half-life of carbon-14 is 1.8 times 10 to the power of 11 second. Got it? That's the half-life. Well, now it becomes kind of easy, I hope. If I know the half-life, maybe I'll just mark on the side here. So remember, from this formula here, I need to find lambda. So I know that there is a relationship between half-life and lambda. So half-life is equal to 0.693 over lambda. So therefore, lambda is 0.693 over the half-life, which is 1.8 times 10 to 11, right? And when I do that, I will get, in this case, let's see, times 0.693, answer, if I did it correctly, 3.84 times 10 to the negative 12 decay per second. There we go. Here's the value of lambda. Basically, I'm done with the problem now, right? So I take that. Now I go back to this formula right here. I'm going to write it down here. So therefore, R equals R naught e to the minus lambda t. R naught is given to me in the problem. It's, I forgot what it is. R naught is, here it is, 3, right? Should be. Right. So it's going to be R. Did I make a mistake here? I want to make sure I'm doing it because my note looked different from mine. 180. Why 180? Oh, okay. Oh, I'm using minutes here. Okay, I got it. Okay. I don't know what is he asking for seconds or minutes? Let me go back to the problem. What will be the decay rate of the sample in the... Pay attention, guys, when you put in the answer in mastering, look at the unit, if it's in second or in minutes. Because my final answer here is in minute. So maybe he wants it in minute, but I'm going to stick with the seconds. So R naught is 3, right? 3 decays per second. E to the minus lambda is 3.84 times 10 to the negative 12. Multiply this by the time, which is, he said, after 1,000 years. Is that right? He said after 1,000 years. So you just take 1,000 years, multiply, convert it to seconds, right? So when I can do it in my head. So that would be 3.15 times 10 to the 3. It's going to be 10 to the 10, correct? Make sense? And then you just plug it in. Let me do that. That needs another calculator for this. I don't mind here. I'm not familiar with it. Hold on. Nope, not this one. I'm shuffling between 3 calculators because one of them doesn't. The one that I use is run out of battery, so I'm using others that I'm not familiar with. Anyway, let's see. I'm going to work on the top first right here. I hope you're working with me as well. So let's see. 3.15 E10 times 3.84 E negative 12 times I'm sorry. Maybe I could pause the video so you don't have to wait for me doing this. And then exponential. There we go. Okay, I hope I got it right. So I got 3.8861. I hope I got it right. Times 3. Final answer 2.65. Kind of look fine to me. So decays per second. Okay. Now, if you do it in minutes, that's where my notes is. It will turn out to be the decay rate is 159. Can I check that? How do I do that? Just take that and multiply by 60. And yep, that's true actually. Yep. So it is correct. Or, so I think I've got it right. 159.5 decays per minute. In my notes, I'm using minutes, I'm not using second. But there we go. Okay, I don't know which answer your mastering notes wanted. So anyway, the second part of the problem, I think I'm going to let you do it. It's not a big deal. So it just basically is, he said 50,000 years. So you do exactly the same thing, except you take the same formula, the same, this whole thing, the same thing, except this becomes what, 50,000 years in seconds. You see what I'm saying? And then everything else is identical, and you just work it out. You got it? And I'll give you the answer for it. The answer is R equal, in minutes that is, 0.43 decays per minute. Okay? All right, good. Then the next problem that I want to do, I forgot, did I say 18? I think it's 18. Okay, let's do 18. And then I think we should be able to, you should be able to do the rest of them on your own, I hope. If not, of course, you can always, you know, ask me. Okay, number 18. Oh, here it is, right here. Okay, it says the common isotope of uranium-238 has a half-life of 4.47 times 10 to the 9 years, so 4.47 billion years, decaying to thorium, which we talked about a bit ago, thorium by alpha emission. Okay, what is the decay constant? What mass of uranium is required for an activity of 1 curie? How many alpha particles are emitted per second by 10-gram uranium? Okay, it looks like a heavy problem. All right, so how do we do it? let's see. Okay, so we have, let's write down the data. Uranium-238, it converts into thorium 234 plus an alpha particle, right? Okay, half-life, he said, is equal to 4.47 times 10 to the 9 years. You got in years, you want to convert to second, I guess. First question, he says, what is the decay constant? Which is what? He wants lambda, the probability the constant. So lambda, well, what is lambda? Well, lambda is 0.693 divided by t half, is that right? And I have everything. So when you calculate that, so 0.693 divided by 4.47 times 10 to the 9 time, convert to second, 3.15 times 10 to the 7. And then when you do that, you get lambda, I'm copying from my book, from my notes, 4.92 times 10 to the 18 decays per sec. Got it? Here it is. All right. B. B says, what mass of uranium is required? Okay, what is the mass of the uranium is required for an activity of 1 curie? Okay. What does he want, really? Okay. Let me get the number of samples. Okay. Now, I'm trying to think about a better how to explain it to you. What's given to us? It is. Let me find, first of all. So I have already found lambda, and I already know the half-life. So I know that the number of samples, well, here, the activity rate R is equal to n lambda. My goal is to find n. That's what I'm trying to say. Because if I find n, I can find the mass. How? You remember? The atomic mass is Avogadro's number. So I need to find this mass if I know n. So if I know n, I can find it, because this is fine, because it's uranium-238. So this is 238, gives you 1 mole, 238 grams, that is, or Avogadro's number. So what mass will give me if I have this number? So I need to find the number of samples. You see what I'm saying? That's basically the goal. So, and I'm going to get it from here. Well, how do I do that? He says, look what he says here, part B. What mass is required for an activity rate of 1 curie? What does that mean? It means R is equal to 1 curie. Well, what is 1 curie? Of course, we don't want to use curie. We're going to use decay per second. Well, 1 curie is 3.7 times 10 to the 10 becquerel, which is decay per second. That's the number we're going to use. So I already know that. Lambda, I just got it from part B, from part A, right here. So I can find n. So n is R over lambda. So that will be 3.7 times 10 to the 10 divided by lambda, 4.92 times 10 to the negative 18. This will give me the number of samples. The number of samples in this case is 7.52 times 10 to the 27 nuclei. Got it? Okay, now here is the argument. Here is how you do it. I know that from chemistry, 238 gram is 1 mole, if you will. We're not doing mole here, but that's, I don't want to do mole, sorry. It's basically Avogadro's number. Is that right? Basic chemistry. Now, what mass will give me this number, n? You cross multiply. You see what I'm saying? I mean, I can do it this way. 238 over Avogadro's number is equal to what mass over n? So 238 over Avogadro's number, which is, what is it? What's Avogadro's number? I forgot it. Let me look it up, sorry. 1.6 something? I'm not a chemist, sorry. Look at the back of the book. Avogadro's number is 6.0223. 6.02 times 10 to the 23rd. The equal mass, that's what I'm looking for, over n. I just got it, it's right here. 7.52 times 10 to the 27. So therefore, the mass, cross multiply, right? So it's going to be 238 times 7.52 times 10 to the 27 over Avogadro. You see what I'm saying? And then let's calculate that. So that's going to be 238 times 7.52 E27 divided by 6.02 E23. Answer. I got this big number. 2. Oops. Go this way. 2.97 times 10 to the power of 3 kilogram. Is that right? Yeah, it's right here. 1, 2, 3, 2.97. Did I get this right? I think so. I hope so. Negative 27. Okay. Then the next step is, once I get that, now how many nuclei? He said the question. Oh, this is it. I'm sorry. This is what the question is asking. He wants what is the number of samples, right here. Let me repeat it again. Let me just. He said what mass of uranium required for an activity 1 curie? It's this number. Okay. Okay. Part C. And he said how many alpha particles are emitted per second, okay, which is decay per second, by a 10 gram of uranium, okay? Well, first of all, you want to ask how many nuclei in 10 grams? You see what I'm saying? Again, we're going to use Avogadro's number. So I'm going to use the same formula right there. Oops. What am I? Right here. This one. Same formula. So it's going to be 238 over Avogadro's number equals the mass. I want to know the mass. I'm sorry. I already know the mass. I beg your pardon. So it's going to be the mass, 10 grams, over what is the sample number, n. So n in this case is going to be 10 times Avogadro's number over 238. So that will be 10 over, let me just calculate it. So that's going to be, what is it, 10 over 238 times Avogadro's number, 6.02 times 10 to the 23rd. And then when I calculate that, I will get 2.53 times 10 to the 22nd nuclei, okay? Now, he said, what is what? He said, what's the activity? What's the alpha? Okay, how many alpha particles per second? What is that? That's activity, R, basically, right? He just kind of in disguise. He said, how many alpha particles are emitted per second? Which means how many decays per second? Well, that's activity. So he's really looking for R. So R, which is lambda n, lambda is a constant. It's always a constant. So we already got that number at lambda. I forgot what it is. It's right here. So we calculate that. So lambda is equal to 4.92 times 10 to the negative 18. Multiply this by 2.53 times 10 to the 22nd. So the activity rate is going to be 1.24 times 10 to the 5th decay times 10 to the 5th decays per second. And there we go. I think I'm going to stop here. This is basically what you need to study for as far as this chapter is concerned. There are some, we're not going to cover fission and fusion. There is it's in there. We're going to touch a little bit on nuclear reaction, which is section 30.5. It's really nothing difficult. Just read it. It's only a couple of pages long, and there is an example that is similar to one of the homework problems. So please take the time to read it. Nuclear reaction 30.5. The rest of the chapter, nuclear fission, fundamental particle, nuclear fusion, everything else is basically skipped. We're not going to cover that. Okay? And that's about it. Okay? Let me know if you have any questions, and have a wonderful week.